Oh, hello everyone. Welcome back to another Learning Glass session. Today we'll learn about the application of the first law to a cycle where we get a mechanical work out from a fuel source or high temperature source and in a cycle so that it always repeats. And the whole point of this is to get high temperature energy from some source and then get mechanical work out. And in many applications of this power cycle, this mechanical work goes to electrical generation from a spinning shaft. Okay, so the ideal Rankine cycle can be applied to many fluids, many working fluids. Steam is by far the most common one. You boil water, that high temperature, high pressure, superheated vapor water gets fed into a turbine where you can get mechanical work. So it's a cycle to extract mechanical work from superheated vapor. What is superheated vapor? It's water in its vapor state at high temperature and high pressure relative to our ambient conditions. So water is liquid in most parts of the earth unless you're frozen. There's some in the air at all times, trace amounts, but if you really heat up this system to high temperatures and within some range of pressures, you'll get all gas phase superheated. And the boiler part of this cycle, the boiler is where you get this energy to bring water from liquid to superheated vapor. And what this cycle is it's four steady flow processes connected in series. It's a cycle, it's an engine, and it repeats to give you a steady flow of work. And we're going to look at this process on a phase diagram of water, and there's many coordinates that you can map out this phase diagram of water, where the actual axes are state variables: temperature, pressure, volume, enthalpy. In this case, we're going to do it on entropy. And within this range of temperatures and pressures that the Rankine cycle operates around, you have this region where you can have either compressed liquid or superheated vapor, or somewhere in between, this mixture of liquid and vapor. And that's what these Rankine cycles typically operate around. And they also operate on two pressure. The simplest ideal case, it can get more complicated than this, and it does to make it more efficient typically. But in this simple ideal case, we're going to have a low pressure branch. So everywhere on this dotted line I'm drawing now, it's the same pressure. So this would be the lower branch, P low, and it's typically around 0.1 megapascals. And the simplest case brings it between a lower branch and a higher pressure branch. So everywhere on this line, it's the same pressure that's higher. So this is P high, and this is typically around 10 megapascals. So in the simplest case, you have four different steady flow processes connected to each other. Each one focuses on a different process where it's either work in, work out, heat in, heat out. And let's start here at this. Typically, the ideal one starts as you have liquid water. And if you have liquid water on this boundary here of this steam dome at this pressure, if it's on this line, this is a boundary between, tipping point between liquid and some gas. This is the saturated liquid line. So state 1 of the water is a saturated liquid state of water. So it's liquid, but it's right at the tipping point. And then what you do is you use what's called a mechanical pump to bring this water from state 1 saturated to compressed liquid. So bring it from a low pressure to a high pressure, and the state changes from the borderline of liquid vapor to compressed liquid state. And one good reason to have this on the entropy diagram is to remind us that in the ideal let's call this S1 equals S2. In the ideal Rankine cycle, the mechanical portions are isentropic, meaning that it has this vertical process from a different state, but the entropy stays the same. And in this case, what we're doing is we're putting mechanical work in. So this is work in at a pump. This is a pump, and it's a liquid pump. So it goes from saturated liquid to compressed liquid, lower pressure to higher pressure at the same entropy. And you want to do that because you can, it's more efficient to heat it up and change the phase at a higher pressure. So the next stage after you go from state 1 to state 2 is to boil it to from the outside, have this water in compressed liquid state, you expose it to a heat exchanger where energy comes in from the surroundings at high temperature frequently. This is applied to coal, power plants, nuclear power plants, and others where this liquid water gets boiled by the coal fire or boiled by a nuclear reaction from the outside. And when you add that energy in from the outside, you keep the pressure the same. So the pressure is going to keep this the same, but the energy will increase, the entropy will increase, and that energy will keep on increasing until the temperature changes here, but it also undergoes phase change here where the temperature stays constant. Then you end up at this final state where the pressure is the same, but the temperature is increased, the entropy is increased, and you end up at state 3 in the superheated vapor region. And the way that you get there is through heat transfer in. So it's a heat engine. The source of this mechanical work we're going to get eventually is a high temperature reservoir, coal burner, or nuclear reaction. And that's all acted upon to this liquid water to boil it to the superheated state. Then, once we have this high temperature, high pressure, high energy, high enthalpy working fluid that went through this, it flowed through a boiler process. Now it's exiting the boiler process at state 3. Then we feed this high enthalpy flow into a mechanical turbine. That's going to get some mechanical work from the change in energy from state 3 to state 4, and this is all going to occur isentropically. So again, it's going to be a vertical line where S3 equals S4, an isentropic process from high enthalpy to lower enthalpy at the exit of the turbine. And the whole point of that is to get from state 3 to decreased enthalpy, and what you get from that is some mechanical work out. So this is what the whole power source, this is where we get the mechanical work out, which we can feed into a spinning shaft into a generator, electrical generator, to get electrical power. So this is a power cycle based on steam, and the source of this energy is this high temperature from the outside. It's always a heat exchanger for a Rankine cycle. It's not an internal combustion engine. It's external combustion engine from coal typically, or a nuclear reaction, which increases the temperature, which allows you to boil this water. Then you feed it through a turbine to get mechanical work out. Then, unfortunately, by the second law of thermodynamics, you cannot go 100%. If you're going in a cycle which is very compact, instead of having a big, huge thing that you go in one shot, all this water goes to mechanical work, all this water energy goes to mechanical work. Instead, you significantly reduce the size and keep on repeating this cycle over and over. If you do that to make it a more compact size, you have to bring this working fluid from these high energy states back to this original state. And to do that, you always have to have in a heat engine some phase of the cycle where there's energy being taken out by heat transfer. In this case, it's after you get the mechanical work from a turbine, you end up with lower enthalpy, but it's still not the original state. So you have to get back to the original state, there's this heat exhaustion step to go from state 4 back to the original state. And in a Rankine cycle, this is the cooling towers, where you lose energy of this out of this. The water comes out of the turbine, but to bring that working fluid water back to the original state, you expose it to another heat exchanger, and typically a cooling tower, where that water loses more energy to go back to saturated liquid from close to being a vapor. It's somewhere in the mixture region, but it's mostly gas. Then you go back to saturated liquid by heat transfer out. So the point of this cycle is in a compact size, for example, the size of like maybe a city block. That would be a big one, but let's say it's like a city block, a small city block of buildings and infrastructure. That's a big engine, but that engine can power a whole city or more. So that's very compact. If you're going to power a whole city, you only need a city block. That's the good thing about heat engines. The bad thing is that the source of this energy is high temperature reservoir, coal combustion, or nuclear reaction for a Rankine cycle. And the problem is that you're not going to get all the mechanical work out. You have to put some work in, and you're going to take an L here, getting the liquid back to its original state to keep the cycle going. Okay, so let's look at this. Let's say for a particular Rankine cycle process, we have given we have P2, or a low pressure branch is 75 kilopascals, and the high pressure branch, it's going from P1 and then up to P2, is 3,000 kPa, and T3 here T3 equals 350 Celsius. So given that, can we use that to find the work in, heat transfer in, work out? So given these, we're going to analyze these 4 steady flow processes individually, connect them one to another. The exit of one is the inlet to the other. So we're going to find find the work in, not in terms of kilowatts, it's going to be kilojoules per gram. Q in, let's call it baby Q. And out. Find these? Yes, we're going to find these. Okay, this is what we're going to have to go with. So let's start with process from 1 to 2. So going from 1 to 2, this is an ideal isentropic pump. And if we were to write the first law for this ideal isentropic pump would be Q minus W equals the mass flow rate times H1 minus H2. That's the first law for an ideal isentropic pump. And if it's ideal, there's no heat transfer. And let's express these in terms of, we don't know the mass flow rate, so let's cancel out the mass flow rate. So this would be negative W equals H2 minus H1. Okay, we know P1, we know P2, but we do not know much else besides the fact, let's say that we're also given from this ideal cycle that this is a saturated liquid. So that's the typical ideal starting point of, the initial state 1 of an ideal Rankine cycle is saturated liquid. So let's go with that, because we need that. We know it's 75 kPa. We don't know anything else besides that it's saturated liquid. So knowing that, that constrains things significantly. So P1 equals 75 kPa sat liquid. Given sat liquid, that constrains us. We know it's sat liquid, so that means that P1 equals P sat, or like, we're going to look for P sat rho on the steam tables, and that will tell us that H1 equals HF at P sat equals 75 kPa. That's what that tells us. That we know that our state is saturated liquid. We know our pressure. That means we need to look for the saturated pressure value of 75 kPa. And then that row on the steam table will give us our properties, especially if we know we're on the sat liquid. That means we need to look at the HF column, and that would give us 384.44 kilojoules per kilogram. Okay? So for the ideal pump, there's no heat loss, and another thing is there's only mechanical work. So ideal pump, no heat loss, we've already considered that. And no T increase. So there's no delta T. So delta H So negative work equals H2 minus H1 equals you can do this a couple different ways, but let's look at it from this perspective. So if there's no temperature change, then the only enthalpy change will be due to pressures and temperatures. Okay, but for liquids, going from saturated liquid to compressed liquid, in many processes, delta V is about 0. It's very hard to change the volume of anything in this phase. It changes, but a very small amount, and that's why we can use this saturated liquid line. As long as we know the temperature, that will change the energy state much more than pressure or volume. Those don't change much. The temperature changes these values. So when we say that, applying this, we can say that the negative work from 1 to 2, let's say that this is 1 to 2, 1 to 2, 1 to 2. It's a good estimate to say that this would be some V, let's call it V1 because we know state 1. So from there, we can get mechanical work because we're relating it to enthalpy change, or we know it's the integral of P dV, but that's going to give you a small pressure change. But from the enthalpy, we can say that because the temperature doesn't change in an ideal pump, there's no internal energy contribution, but there is this PV contributions. And if you take another assumption that the volume, you can ignore the volume change, then all you need is V1, which we do know on the steam table. So from steam table, from here, V1 equals Vf at 75 kPa, and that is 0.00104 meters cubed per kilogram. That's from the steam table. So now we know V from the state 1. We're taking this assumption that it's ideal, so there's no heat loss. So that means there's only a PV change, and then the V does not change. So that will allow you to get from the enthalpy change the mechanical work in. And if we were to plug those in, we would get negative W from 1 to 2 equals 0.00104 meter cubed per kilogram times, we're given P2, 3,000, P1, 75, so this would be 3,000 minus 75 kPa, which is 1 kPa is 1 kilonewton per meter squared, and then 1 kilonewton, well, we want kilonewton, so this is good. So kilonewtons is what we want because that's related to Newton meters, and the kPa's cancel out. There's 1 meters left here, these cancel out. So now we're in kilonewton meters. That's kilojoules per kilogram. That's good. So this would give us so our work would be a negative value if we brought this negative here. So that means this is work in. That's good. We found work. All right. So we found the work in using the fact that for compressible liquids, the volume doesn't change much. You can then use the fact that an ideal pump, the temperature doesn't change. And that would give us this V delta P. So that gave us the work in. Okay, that's good. Now, if we want to find, let's move on to the next stage for a second, and I'll show you we're going to come back to the first phase process though. So if we wanted to find the heat in, we would apply the first law. So let's go ahead and start that. So for 1 to 2, this is a isobaric heat in boiler. So you're boiling water and you want to input energy so that the phase goes from compressed liquid all the way to superheated. So this would be from 1 to 2, 2 to 3. There's boiler has no moving parts, so there's no mechanical work. And the pressure stays the same, so the P2 equals P3, that's what we know. And so one question is, how do we find, so what we need is the mass flow rate. We're going to instead go per mass, so we're going to cancel the mass flow rate. We do not know H3 and H2 yet. Maybe we can. We might be, actually we know that P3, so we know that P3 equals P2 equals 3,000, and we know that T3 given equals 350C. So that actually is enough for us to pin down the phase. We know the pressure, we know the temperature. We can test that on the steam tables to see whether it's saturated liquid somewhere on this border or somewhere in between. And if, depending on where those lie, it's either going to tell us that we're there, or we're compressed liquid, or we're superheated vapor. So these two are enough to give us H3 actually, in terms of pinning down what table to look for, and then that will give us the H3. So we can find H3. We'll do that next. But the question is, do we know H2? We only know the pressure. We know that it's 3,000 kPa. We do not know the temperature, but we do have the first law of thermodynamics. So here it's where we said the temperature does not change much, but there's this PV term that we can estimate from here. We can say we can say U2 equals U1, and then add this PV term, V2 equals V1, or the same thing it's basically the same thing. That's just going from here, that we know the enthalpy, we know the work, so we can say that H2 from process 1 to 2, going back, so H2 is H1 minus W from 1 to 2. So we found negative W is 3. So that is 3 here, that including the negative. H1 is this. So this would be it's minus W is 3, so this would actually be plus. So there's higher enthalpy because it's higher pressure going from state 1 to state 2. So negative W is 3, so that's why it's plus here. So H2 we're going to need that. So yeah, we can find heat in now because we know we're going to find H3 on the steam table soon. We found H2 from the previous process. We can either just plug it into enthalpy, making the assumptions that U2 equals U1 because the temperature does not change, and V2 equals V1 because the volume does not change. So that change in enthalpy will just be due to the change in pressure. That is the, and that is what we did to find work. So we'll just simply plug this work in that we found based on the same assumptions. And it's effectively the same thing, just different steps slightly. It's just basically the same. Okay. So let me erase this and focus back on to this H3 now. We don't know H3 in terms of the enthalpy number, but we do know that we can find it based on the given temperature at T3 and the fact that it's an isobaric heat transfer, so that means the given P2 is the same as P3. So now that we know P3 and we know T3, we can go on the steam tables and see where we are, whether we are saturated liquid first, and that test will tell us whether we are there or we are superheated or whether we are compressed. And spoiler alert, a typical ideal Rankine cycle is designed to boil all the way to superheated steam. So we'll confirm that. I think I have this confirmation. So yeah, spoiler alert that if we are at P3 is 3000 Kelvin, Tsat is less than 350. So we are superheated vapor. I don't know what Tsat is, but let's just say that that's the test we did. We say that P1 is known, P2 is known. That means for an isobaric heat transfer, we also know P3. So looking on the saturated liquid table, saturated vapor table, saturated mixture table, if we look at P3, what we will find is that the T saturated is much less than 350 Celsius. That means that our temperature is too high to be a saturated condition. That means we have to be superheated vapor condition. So I'll leave it to you to double check what the actual saturated temperature is. And you would find that the saturated temperature for pressure of 3000 Kelvin is lower than 350. Because that's the case, we have more energy and we are superheated vapor. Okay, so given that this gives us superheated condition, we'll look on the steam table for superheated vapor at this pressure and this temperature. That will give us that H3 is superheated. That is 3116.1 kilojoules per kilogram. That's H3. So that will give us Q3. So Q from 2 to 3 equals H3 minus H2 equals 3116 minus 387.5. And I didn't round those off here, but I have a rounded one here, 2728.6 kilojoules per kilogram. So that's the heat coming in. This is heat in. It's positive, so it's heat in. Okay, so that is, we went from state 1 to state 2, found the work, went from state 2 to state 3 to find the Q in. All right, now let's find the mechanical work out of this turbine. So from state 2 to state 3, this is an ideal, state 3 to state 4. State 3 to state 4, this is an ideal isentropic turbine. And applying the first law to this, it's ideal, there's no heat loss, there's no entropy, it's isentropic. So we need to find the mechanical work from here. So that would give us negative, canceling out the mass, negative work from 3 to 4 equals H4 minus H3. We know H3, we just found it in this, we found it in this analysis from the steam tables that P3 and P2 is given. That's good. So now all we need is H4. Okay, so what do we have to go on? We know T3. We already used that. That gives us T4. We do not know the only thing that we do know is that in an ideal Rankine cycle, that P1 is where the pump inlet is, but what happens in the cycle to get back to the original T1 is that it's an isobaric condenser process where this exhaust of a cooling tower, whatever this phase change happens in the actual power plant, the ideal case is an isobaric heat transfer out to change the phase. So we know that P4 equals P1. That's one thing we do know. P4 equals P1, which is 75 kilopascals. That's one thing we know. I'm not sure if we need that. Another thing that we have not used for this pump, sometimes you need it, but in this case we need it for this turbine, is that this is isentropic. So S3 equals S4. S3 equals S4. What is S4? It's S3, so let's find S. We know we can find S3. So from the superheated vapor, S3 going back to the steam tables for this 3 state is 6.7450 kilojoules per kilogram. Well, from this isentropic case, this also equals state 4. Okay. So the way that we're going to use this is that's our first connection into state 4. We know that the entropy has to be the same as state 3. This value on the superheated steam table allowed us to find S3. That has to be the same as state 4. But the difference is that S4 might be at a different state. Again, spoiler alert, typically it's within this dome here, but let's verify that. So if we know that 6, so at PSAT equals 75 kPa, SG, if you're within this dome, that means that the entropy you have is either the same entropy as the saturated liquid line, or it's the same entropy as the saturated vapor line, or somewhere in between. So if we look that up, at 75 kilopascals, SF is let's call this state 4. This would be 1.21 kilojoules per kilogram Kelvin. That's entropy units. So our actual entropy has to be 6.75, let's round it off to. And for the gas, let's see, what is SG? This would be 6.95 kilojoules per kilogram Kelvin. So that means because the actual entropy that we are from the isentropic process is in between here, that means we are a saturated mixture. Okay, if we are a saturated mixture, the next question is, what is the quality? Well, the quality can be found from our weighted average, where S4 has to be a weighted average between SF4, we're at 75 kilopascals, so the entropy at the vapor boundary plus the quality, which tells us the proportions, and the vapor boundary So that's how you find the weighted average of this vapor versus liquid components. Then we can use that to find the quality because we already know what S is. So this would be 6.75 minus 1.21 over 6.24. That will give us a quality of 0.0 .8861 kilojoules per kilo. Oh no, this is no units. So this is quality at 4. That's good. Then, because it's a mixture, both the entropy is a weighted average, and we use that connection between state 3 and state 4 to find the quality, because we can look up the limiting cases, but we're somewhere in between. That allowed us to find the quality. Next, we can find the entropy from this relationship. So H4 equals H of the fluid floor plus the quality at 4, and this difference, Hg4 minus Hf4. And when we do that, looking up those values, H4 equals 2403.0 kilojoules per kilogram. That's H4. Then, applying the first law here, that means that negative W, we know we just found H4, we knew H3, so H3 is bigger than H4, so that would give us a negative 713 kilojoules per kilogram. So that means indeed work out. The number we got is positive for W. That means it's work out. All right, so we found the work in, heat in, work out. What is the Q out? Well, we have everything we know. This is called the condenser stage. 1,4 condenser. There's no mechanical work, so it'll be the heat transfer from 1 to 4 equals H1 minus H4, because we're going from the outlet of the turbine state 4, from 4 to 1. So the final state is 1, back to the original state, and we have everything. We found H1 earlier, I erased it. We just found H4, so that would give you the Q from 1 to 4 is negative 2019 kilojoules per kilogram equals Q, so that indeed is heat out. All right, this is heat in from 1 to 4 is heat out. So what did we learn here? Well, what we learn here is that heat engines, these are typical values. This is an ideal cycle, but as we said, these pressures are typically 1 megapascal to 0.1 megapascal. That's kind of what we had here. And for steam, that constrains the temperatures, 350 Celsius, that's on the steam table as superheated vapor. That's how a real cycle works. You boil it. It's called a boiler because you boil it to the gas phase. There's always this mechanical work in to go from the low pressure branch to the high pressure branch. And the whole point of this is to get a high enthalpy steam to flow through a turbine and to get mechanical work out. So this is a heat engine. We don't do this a lot in California. In San Diego, we used to do this at the nuclear power plant in San Onofre to use a nuclear reactor to boil water. This heat in came from a nuclear reaction, high temperature to boil the water to bring it to superheated vapor. That's the only, we do that up north in California as well, but in many other parts of the country, many other parts of the world, they use coal to burn coal to get a high temperature to boil steam to get electricity. So our source of the power grid for electricity in California could be 1 or 2 nuclear power plants in the Rankine cycle, but many parts of the world and the country we use a Rankine cycle to burn coal, and we burn the coal to power a Rankine cycle for steam. Okay, where does that electricity go? What happens is, for this typical conditions, even with a lot of these assumptions, these are pretty typical values, that all that for that, you boil water with 2,700 kilojoules per kilogram of water, but you only get 700 or so mechanical work out. You have to put 3 kilojoules per kilogram in, so you get around 700 out. You put in 2,700, and what's worse is that you lose about 2,000 of that. So heat engines are good because we can make a compact engine the size of a city block, can power the whole a city or more, or a whole county from the size of a city block. That's pretty compact. And these fuels are relatively cheap. Coal is cheaper than solar power, cheaper than batteries. There are downsides that we're probably going to have to figure out. Nuclear power is not as cheap. It can get cheaper and cheaper, but there's no CO2 emissions, so that's good. So the problem, though, when you're going through this cycle to get this mechanical work, it's compact in this closed loop of water, working fluid, but you only get maybe like 1/3. What is this? Not even 1/3. This is like 1/4 here of the energy in mechanical work. So that's heat engines. We'll talk about more about that, how that relates to the second law of thermodynamics. With this, we only use isentropic processes and the first law of thermodynamics. So thanks, and I'll see you again next time.